points on this geodesic or quasi-geodesic stay close, bounded by some constant, uniformly over the entire length of the geodesic. So we have this picture, here you pick some point x, you pick some point y. You have a, I call it LA quasi-geodesic. Different notation, so this is an LA quasi-geodesic. Quasi-geodesic. Right? And the criterion was that this bound was given by n LA, so this is less than n LA, so they stay close. And that's uniform over the entire length of the geodesic. So that was to illustrate that. Okay, and something I'm going to do in this talk, I'm only going to talk about finitely generated groups. So everything I do will be in a calligraph of group. And if we talk about groups, there is a different notion, which is related to Morse geodesic. So you take some element G and G, and there is a notion of a Morse element. And so this G and G is called Morse element. If you take the cyclic subgroup generated by it and you embed it into calligraph of G, then this gives you a Morse quasi-geodesic in a calligraph. Quasi-geodesic. Okay, now it's maybe clear why I'm talking about quasi-geodesics, because if something is a geodesic in a calligraph with respect to one generating set, it is a quasi-geodesic with respect to a different generating set. So if you want to define an element as a Morse element, you can only say it has to be quasi-geodesic because if you change the generating set, it should not change the fact that it is a Morse element. You don't want that. You want it stable and then change finite generating sets. Okay, so Morse geodesics, Morse elements. Matt nicely called them hyperbolic directions, which is a good term. So these were the hyperbolic directions. Okay. And what are examples? The prime example we've heard in several talks now are hyperbolic groups or hyperbolic spaces. So what's in hyperbolic groups? Every geodesic was Morse. Every geodesic Morse. And now that we have this new definition of a Morse element, we can also say that in a hyperbolic group, every element of infinite order is a Morse element. I generally mean by infinite geodesic or geodesic ray. Otherwise, I will call it a geodesic segment. So in this case, the definition of a Morse element, if I restrict to by infinite, then it gives us that if you want the embedding of a cyclic subgroup to be a by infinite quasi-geodesic, this element needs to have infinite order. So let's put this here. G has infinite order. Okay. So that's the setup for this talk. And as the title says, Roman and I, so this is photographed with Roman Tessera, I've written it down, but I haven't said it. We looked for those Morse geodesics in lacunary hyperbolic groups. It's a nice, fun thing to do, but why particularly in lacunary hyperbolic groups? So for this, I'm going to start just saying what type of group we can find there, and then define what lacunary hyperbolic groups are. So, an example of a lacunary hyperbolic group. Okay. There are unbounded torsion groups within that class of group. Torsion groups. about it a little bit. I think Matt might have said it, or someone might have said it. If you have a Morse geodesic, having Morse geodesics is quasi-isometry invariant. If you have a Morse geodesic in one space and you have a different space, which is quasi-symmetric, it will have Morse geodesics. With Morse elements, the situation is not clear. It's not known whether if you have a Morse element in a group, and you have a group which is quasi-symmetric, does it have to have a Morse element? You see the Morse geodesic coming from the Morse element in the other group, in the other calligraph, but you don't know whether it comes from an infinite order element or whatever algebraic structure is underlying there. So the question we had was whether you can have Morse geodesics in torsion groups, and that's the reason for this talk. So we looked at these unbounded torsion groups coming from that class of recurrent hyperbolic groups, and we exhibited Morse geodesics in it. So if you have unbounded torsion, it means every element has finite order. So this group can't have Morse elements. But it has Morse geodesics, and I'm going to show you how and why that actually matters and what you can use it for. Okay, so let's put that down here as more, it's less general statement, so this is with Valma. There exists an infinite torsion group with Morse geodesics. That's what we have, and for those of you who know a little bit, I'm going to mention it later again. So unbounded torsion that we have in this case is the best you can hope for. There can't be a Morse geodesic in a group with bounded torsion. That's for reasons to do with asymptotic cones, and we may have time to talk about that later. So that's the best you can hope for, unbounded torsion and Morse geodesics. Okay, so what are Lucomery hyperbolic groups then? So we hear beyond hyperbolicity, so the name of the group more suggests a little more that it's a special case of a hyperbolic group. That's not the case, it's a more general term. So Lucomery hyperbolic groups. This is using what Dennis was talking about this morning. There's a classification by Olshansky Ozitsapia, which tells you that if a group is Lucomery hyperbolic, it is a limit of hyperbolic groups. So the formal definition for this is points. So you require one asymptotic cone is an R-tree. Okay, so Aditi was talking about asymptotic cones, which is really nice. I can use it now and I don't have to go too much into details. And she also mentioned that if you have a hyperbolic group, every asymptotic cone is an R-tree. That's an if and only if. That's a statement by Gromov. And for Lucomery hyperbolic groups, we only require one asymptotic cone to be an R-tree, and everything else, every other asymptotic cone can be whatever it likes to be. So this is the beyond hyperbolicity part of this talk, so generalizing this. And so there, as I said, there's this classification that if you follow our equivalent, so this is by Olshansky. Goes in up here. leave out the very technical parts here. So you have G0, then you have an epimorphism alpha 0, G1, alpha 1, G2, alpha 2, and in the end, you have some group G infinity, which we call G here, like Dennis did this morning, which is the limit of those. And the condition that comes in here is the injectivity radius of these maps alpha I. So with, this is now the criteria we need. So delta, let's call it like that. Yeah, delta I is a little o of the injectivity radius of alpha I. So each of those, so Gi is delta I hyperbolic. And this RSI, which the generating set is the injectivity radius. Okay, I'll draw a picture to illustrate what this means or how we can imagine this. So you start with the group G0, and inside this ball of radius RS0 alpha 0, this will never change. And then whatever quotient you form, this ball remains the same, and then outside hit your group G1. So here in here you see delta 0 as hyperbolicity constant, and here you see delta 1, and this keeps growing. 2, you see delta 2. And this condition here says that you have a bolicity constant you see in these finite balls is much smaller than the injectivity radius. So the balls that remain untouched are much bigger than the fattest triangle we can find inside these pictures here. Okay, so this is how we can imagine those. And how can you generally find a Morse geodesic in this? So we don't know much about these groups. So the construction, that's when I have to talk about the construction of these torsion groups. That's the case I'm going to focus on. The construction of Lacunary hyperbolic groups using this by forming small cancellation quotients is much more general. The interesting case here is the torsion case, because for other Lacunary hyperbolic groups with small cancellation condition, it was already known, or was a result by Olshansky and others appeared, that they do contain Morse geodesics via using infinite elements. And the torsion case is the more interesting one. So what do? You start with, for the purpose of this talk, we start with the free group to make everything easy. So generally X and Y. And you list all the elements. Start with X1, X2, X3. Okay, and so it's a countable group, no one stops you from doing that. And then every time you pass from one group to a quotient, you add a relation by this small cancellation criterion that if you're interested, please do ask me. I'm happy to talk about it after the talk. So you take quotient by adding a power. So you take your first element, x1, and the small cancellation tells you if you raise this to a sufficiently large power, so to some power n1, and you quotient out the normal separate generated by this, then this group is again a hyperbolic group with a hyperbolicity constant delta 1, and that has other nice properties. So this is again hyperbolic. Okay, and then for the next step, so we have the same setting as what we started with. We started with a free group, which is a hyperbolic group. We add a very large power of one element, so there's a relation, and then we have a new hyperbolic group, which, so we've killed this element in our list, it now has finite order. Now we go pass on to the next one, so we take G1 and quotient out a an even much larger power of the next element. Okay, so what do we use in here? So small cancellation requires mi to be very large. Okay. In particular, something similar like the limit of mi divided by mi plus 1 has to be 0, so they have to even become much bigger. Okay, so that's taking some parts of that technical small cancellation and just applying it to this case of the torsion group. Okay, so that's the one thing. And so this is again, this is delta, where are we? The delta 2 hyperbolic. And we keep going until we get G infinity, which we call G. And also the hyperbolicity constants, delta I, they are all over the place, they're just growing. So group G infinity is obviously not hyperbolic anymore, it's not finitely presented. In fact, if you require that one asymptotic cone is an artery and you require a group to be finitely presented, then it's resulted by Kaplan-Kleiner that the group has to be hyperbolic. So finitely presented and one asymptotic cone, an artery, is enough to make it hyperbolic. So everything we talk about here, which are the more interesting cases of polyclinic hyperbolic groups, they're all infinitely presented. So let's put that down. G infinity is infinitely presented. Okay, so we have a rough idea now what our group G infinity, this infinite unbounded torsion group, looks like. What kind of relations does it have? Just large powers. It does not tell us yet how we're going to find a Morse geodesic. That's unfortunate. But we can use asymptotic cones again. So there's a statement by Cornelia Trutu and Marx here. Says that a geodesic is Morse. We're going to abbreviate their original statements, are very long. Geodesic is Morse, or quasi-geodesic. Morse, if and only if G, if the limit of G in every asymptotic cone, so not just one, every asymptotic cone, is such that, now we have two conditions. So the first one says, in the limit, every point of this limit geodesic in the asymptotic cone has to be a cut point. Limit, let's call it LG. Every point of LG is a cut point. Okay. Unfortunately, that's not enough. There's a second part, which breaks LG into two parts, obviously. Which obviously every cut point on a limit does because it's a geodesic. But those two parts have to lie in two different connected components. Lie in two different connected components. Okay, so this is, if you don't know what the asymptotic cones of a group look like, it's a nice statement but not helpful. But luckily, with this powerful thing called small cancellation, we do know what all asymptotic cones of these groups look like. So that's also a result in the paper by Olshansky-Nositz up here. So put that down. So this is again Olshansky-Nositz up here. If G satisfies and I'll call it a graded small cancellation. This is the correct term. So in every step we have some sort of small cancellation condition. That's all we need to know for the purpose of this talk. Graded small cancellation. probably tells you as much as you knew before I wrote that down. So what's a circle tree? A circle tree is a tree-graded space with respect to circles. And for those of you who don't know what a tree-graded space is or have never heard that before, you take some tree and you're allowed to attach so-called pieces. So you have pieces of the tree-graded space. Are circles, and I'm going to say it but not write it down, circles of uniformly bounded diameter from above and below, so you also have control over the size of the circles. So you have these pieces here. Oops, sorry, that circle. My drawing skills are not very good, as you might have noticed by now. Here's one. So you're allowed to have these pieces going away, but there are also conditions on that. So you have these so-called fat parts of the tree, and there's more lines going away from it. And the rule is that, first of all, every of these pieces has to be a circle, and two circles can only touch at most one point. So, two circles can only have at most one point in common. That's the first one. And every geodesic triangle, every closed simple closed loop has to line a piece. So every loop is in a piece. Okay, so those are your conditions. You can't have any loops outside these pieces. You're allowed this special set of circles. And you're allowed loops within that set, but everything else has to look like a tree. Okay, so we know every asymptotic cone of this construction up there, this unbounded torsion group, looks like this. Okay, where does the liquidary hyperbolic part come in with the artery? That's the degenerate case when the set of pieces is empty, then you get an artery. So for certain asymptotic cones, you get an artery, depending on the scaling sequence, or an anti-ultra filter, and for others, you get pictures looking like this, very simplified looking like this. Okay, so now we have a picture of an asymptotic cone. We can use the theorem by Fruitus up here to determine which paths in the asymptotic cone come from Morse geodesics, and then once we've found the possible path here, we can try to play it back into the calligraph and check whether that actually gives you Morse geodesics. So that's the strategy. We're exhibiting the path in the asymptotic cone, and then we're trying to puzzle around and find the path in a calligraph, which gives you a limit looking like that. Okay, so what are the good paths here? And what are the bad paths? So it says we're in a group, so by the way, every point is a cut point in the asymptotic cone because we're in a homogeneous nice space. So every point is a cut point. That's an easy condition. So that's a check. The problem is more the second one. So if you take a path, the limit has to break into two parts. So if you take a path, then you go here, here, and then you go here, and then you go there. And possibly you come from there. And you take this part out, it's a cut part, take it away. Yes, the right path has broken into two pieces, so we have this chunk and that chunk, but they're connected through the arc going through the circle here on top. So this is a bad path. This is not going to give you Morse geodesic. So instead of this, you can only jump between the circles. So the green path here, corrected version, you can touch the circle at one point, but only one single point. Okay, so let's write that down. The path in the asymptotic cone. And only touch. I'll put it like that. Touch surface. Okay. So those are the paths in the asymptotic cones. And now we are trying to avoid those in the asymptotic cone. So where do the circles come from? Okay. So it was one of the nice pictures that we drew. If you have a circle in the asymptotic cone, so here is the asymptotic cone, and you have a circle. It comes from a sequence of kind of circles. So we can think of them as circles. They can be quasi-geodesic, they don't have to be nice and round, they can be a little bit bruised. So you have the sequence, there's a circle, circle, bigger circle, and an even bigger, and so on. And then in the limit, it gives you circle and asymptotic cone. So these are circles of radius, and the radius has to match the scaling sequence. If you see loops, repeated loops of radius scaling sequence you're looking at for this specific asymptotic cone, you will get a loop of the corresponding size in the asymptotic cone. So these are circles of radius matching the scaling sequence. Okay, so that's for one asymptotic cone, and then depending on the scaling sequence you choose, you pick up different circles in a Cayley graph, and this is also how you get an R tree. If you choose a scaling sequence which just doesn't match up any pattern of circles you observe, then you don't see anything and gets an R tree. Okay, so we see circles in a Cayley graph. The circles in a Cayley graph, they're loops coming from relations. Okay, so every time we add a high power of an element as a relation, we add a new loop in a Cayley graph, we fold it up, and if we do this for every element, so we have this pattern, and if the powers of these relations that we choose match up the scaling sequence, then we get a nice circle in this asymptotic cone. So the task here is to avoid loops coming from relations in the Cayley graph, and then the limit will be a nice path like the green one here. Okay, so avoid loops